Okay, well, while that's up there, I'm going to introduce Dr. Mitch Goldberg. He is our co-chair. Mitch has over 18 years of working with NOAA and is our JPSS short course co-chair, along with Dr. Jordan Girth. Mitch is our JPSS Chief Program Scientist and former Chief of the NESDES Satellite Meteorology and Climatology Division. At JPSS, Mitch serves as an independent expert and representative of the science and user communities that are responsible for ensuring the scientific integrity of all stages of satellite development. Mitch has received multiple gold and silver and bronze medals from the Department of Commerce, as well as the NOAA's Administrator's Award for Leadership in developing the International Global Space Intercalibration System. He's also a recipient of the University of Maryland Most Distinguished Illuminous Award from the Department of Atmospheric and Oceanic Science. So if everyone has the website up, I'm going to go ahead and continue to the next slide presentation for Dr. Goldberg. At this time, I'd also like to introduce, and Jordan's going to be kind of guiding us as well, Dr. Jordan Girth. Jordan is an associate researcher with NOAA's Cooperative Institute of Meteorological Satellite Studies at the University of Wisconsin Space Science and Engineering Center. His role with JPSS is to develop and support user applications for satellite imagery and products, particularly outside of the contiguous United States. He is actively involved with training the National Weather Service meteorologists on the next generation of geostationary and polar orbiting satellites, and helping install and maintain satellite tracking antennas on islands of the Pacific Ocean. So at this time, I'm going to introduce Dr. Goldberg's presentation. There you go, Mitch.
Thank you. Thank you, Christy. So, well, welcome to the AMS short course. We have a great agenda today covering a lot of aspects of JPSS. So I'm going to give an overview to talk about JPSS and what it means to basically to the nation and also to the world. So JPSS, on November 18th, we had the launch of JPSS-1. It's our very first operational, truly operational satellite, next generation for NOAA. And now it's NOAA 20 since it's reached its successful orbit. So we're very excited now to have NOAA 20, which will be in orbit along with SUMI MPP. So what are polar satellites? Polar satellites, they fly in a lower orbit. You know, it's different from geostationary. So a polar satellite orbits the Earth about 512 miles above the Earth's surface. It orbits from pole to pole, and while it's orbiting, always in the same racetrack, the Earth is rotating underneath it, and that's how we get global observations. And these global observations are really critical for weather forecasting out to 7 days. So that's a criticality of JPSS. It's really providing a window into the future, you know, being able to forecast extreme weather events out to 7 days. While geostationary basically orbits around 22,300 miles above the Earth over the equator, and it's moving at the same speed as the Earth is rotating. And so it's watching weather as it unfolds. So it's very important for NOAA and the United States and the international community to have a constellation of both geostationary and polar orbiting satellites so we can forecast weather out to 7 days, and we can see weather as it unfolds. Now, it also does a lot more than just weather forecasting. It also has great coverage over the polar region. Alaska uses polar satellite data like it was geostationary because it has a better spatial resolution and good temporal refresh. And so this is just a movie showing how SUMI MVP and JPSS, or NOAA 20 now, they're 50 minutes apart. We'll have twice the amount of data. And also, there's a lot of other benefits by having them 50 minutes apart, which I'll talk about shortly. So JPSS is a core component of the weather forecast enterprise. A lot of people don't know this, but 85% of all data that's used in weather forecast models are from polar orbiting satellites. On the left is a really good forecast of Hurricane Irma. Tuesday morning, I think that was September 5th, the forecast 5 days later, Sunday morning, showed the position of Irma at Key West, or near Key West, and it was an exceptional forecast. And that forecast was allowed emergency responders to prepare, right? FEMA, state and local governments, you need plenty of time to evacuate, to pre-position assets for, so the recovery can start right after the storm passes. So Florida had plenty of time to evacuate, and it was a very successful emergency response to that hurricane. And polar satellite data, of course, contributes a lot to that. On the right is a pie chart that basically looks at different observation types that's attributed to forecast error reduction. This comes from ECMWF, but it shows that the microwave and infrared sounders, hyperspectral infrared sounders, those two data sources contribute to about nearly 60% of the data that's been attributable to really reducing forecast error. And that's because the microwave and infrared sounders have something in common. They observe the atmospheric temperature and water vapor information. And that's really the key ingredient needed to do a good job in forecasting weather out to 7 days. There's been a lot of successes over the past couple of decades, and that is shown in this chart that shows the evolution of the ECMWF forecast scale, which the NCEP, National Weather Service forecast scale is very similar. So what this chart shows is an improvement of the 3, 5, 7, and even the 10-day forecast over time from 1981 through present day. This is the 500 millibar geopotential height anomaly correlation, which is highly correlated to steering currents. So for example, if you have a disturbance out in the Pacific, you need to really understand the steering currents in order to know where the storm will be ending up. And so 500 millibar geopotential height is a good score, a good measure of that information. And that's really key for predicting where the storms are going out to 7 days. So you can see back in the early 80s, the 5-day forecast was not so good. It was about, maybe 65% correlation, almost, 50% would be like flipping a coin. But also, during this time period of the 80s, there was a large separation between the northern and southern hemisphere in terms of skill scores. So the upper curve here, this dark curve here, is anomaly correlation skill for the northern hemisphere, and the bottom lower one is for the southern hemisphere. So you can see a big separation in skill. And then something happened around 2000. The separation between the northern hemisphere and southern hemisphere vanished. This is attributable to better use of satellite data, better satellite observations, and also the model having higher spatial resolution. And also weather service, some NWP centers like ECMWF went to 4D VAR, four-dimensional variation analysis. This shows the spatial resolution of the models as a function of time. So back in the early 80s, the spatial resolution was only about 210 kilometers, very coarse spatial resolution. So you can imagine that would be attributing to reduced skill and forecast. Then in the early 90s, the resolution got a little bit better, still fuzzy, 63 kilometers. Then in the early 2000s, 39 kilometers, roughly. Then later became 16 kilometers in the early 2010s. And then today, 8 to 10 kilometers. And that's impressive. So now so at 210, you didn't even know what you were looking at. And now you can clearly see, starting at 39 kilometers, you say, well, maybe I'm looking at a hurricane. 16, you're definitely looking at a hurricane. 8, you can really resolve things. So a couple things happened during the early 2000s. We've had our very first, or late 1990s, a microwave sounding unit called AMSU, which was much more capable than the early generation called MSU. AMSU had 15 channels, atmospheric temperature channels, throughout the atmosphere, so providing good information there. We then, in the early 2000s, we had the first hyperspectral infrared sounder called VIIRS from NASA. And then in the mid-2000s, we had EASI, a European hyperspectral infrared sounder from EUMETSAT. And then at the same time, we've started to have multiple orbits, a lot more orbital data. So we had, during this time, NOAA 15, 16, 17, 18, 19, and plus the Aqua, plus 2 MEDOPS, now later on SUMI NPP in 2011, and now JPSS NOAA 20. So we have very good coverage, and that's attributing to the improvement in skill score. So it's a remarkable improvement. So from the 1990s, we basically, to present day, we extended the 3-day forecast out to 5-day in terms of the accuracy. So now we have very high confidence in the 5-day forecast. Back in the 1980s, no one would show the 5-day forecast on TV. Back in the 1990s, no one would show the 7-day forecast on TV. Now we have confidence in the 7-day forecast, and of course the 10-day forecast is still flipping a coin. But anyway, good progress. So it's been a big success, combination of the weather prediction, numerical weather prediction community, plus the satellite community. So we always say that polar satellites is really the backbone in terms of observations to the forecasts, to the numerical weather forecast. And this is an example that ECMWF did for Hurricane Sandy, if you recall, that hit the coastline of New Jersey. And this is a 5-day forecast, and this is with polar satellite data, and this is without. So you can imagine if you didn't use polar satellite data, the forecast would be, the 5-day forecast would be saying that, oh, you don't have to worry about this hurricane. And then you wouldn't have enough time to prepare for evacuations. So that's also illustrates the importance of polar satellite data. We also have excellent coverage in the polar regions, which I mentioned earlier. We have an instrument called VIIRS, which has a day-night band, which can actually, it's like a visible instrument that operates at night using lunar illumination, so we moonlight reflection from the moon, and so we can see ice. On the right is just an infrared image showing how we get great coverage in the polar region, and also we can track winds, track clouds, and get wind speed. This is our program for JPSS, for the JPS series. SUMI NBP, which was launched back in 2011, was really a research satellite mission that worked so well that we made it operational at NOAA. So it is it will become our secondary satellite, operational satellite after NOAA 20 is commissioned. And then you'll see that there's a series of these JPS satellites, basically with the same instrumentation. And so, which means that we have confidence now that we'll have this long time series of JPSS data for the next 20 years and even beyond 20 years. So that's good to know. So when we make an investment on how to use the data, that investment will be with us for a long time. And then, of course, we still have our older satellites still operating, NOAA 15, 18, 19, SUMI NPP. We also have the MEDOPS series, which are not shown on this chart. So these are instruments on JPSS. This is what the satellite looks like. I'll go through each one quickly. So ATMS and CRIS, they are the sounders. ATMS, and both ATMS and CRIS, they're really looking at thermal energy radiation being emitted from the Earth's surface and the atmosphere. ATMS is a microwave sounder, so its wavelength is larger than the infrared, and it can see through clouds as long as there's not precipitation. So you get this almost all cloud cover, all, I guess, weather conditions of getting atmospheric temperature, water vapor. But it is affected by precipitation, which is good because that allows us to see where it's raining. And it's also affected by sea ice, so we can see through the clouds and we can see sea ice and snow cover as well, so that's good. CRIS is a hyperspectral infrared sounder. It sees higher vertical resolution temperature and water vapor information, but because its wavelength is shorter, smaller, it's impacted by clouds, so it can't see through clouds. But we use the microwave to help cloud correct the infrared, so we actually use them together in our algorithms. And also CRIS Can also provide information on trace gases like CO2, CO, methane, and things like carbon monoxide and so forth. VIIRS is an imager radiometer suite, visible infrared. It basically provides our key environmental intelligence. So it's having like a high-resolution camera in space, operating the visible, near infrared, and infrared. It has great spatial resolution, 375-meter resolution. It has a technology of oversample detectors, so that when we scan out from nadir, the spatial resolution doesn't really degrade that much. Only we go from, for example, 375-meter at nadir, we'll go out to 750 at the edge of scan. And the swath is about 3,000 kilometers. And it does a lot. I'll show an example of a lot of different products, but it does ocean color, for example, aerosol, smoke plumes, health of vegetation. We have OMPS, which is an ozone sounder. OMPS mapping and profile suite basically does ozone, monitoring ozone hole. Also, the data is used for UV index forecast, and also does things like look at aerosol plumes from volcanoes and SO2 plumes. And finally, Ceres is Clouds and Earth Radiation Energy System, and it does Earth radiation budget studies, looking at outgoing long-wave radiation, reflected solar. So that's basically our lineup, and so it's a pretty good, impressive lineup. It actually covers the entire, spectrum that's used in remote sensing today, from UV all the way to from UV, visible, near infrared, infrared, and microwave. So these are what the next generation instruments look like. So from 18M, so it's an improvement. Remember, this NOAA 20 is now a replacement. It's a follow-on to the earlier NOAA Polar Satellite series, which basically had an AMSU versus is now an 18MS. So 18MS has better spatial resolution, better coverage. So this is an AMSU coverage versus 18MS. So you can see that with AMSU, we had gaps. This is for, I think, Hurricane Sandy, looking at the warm core at 250 millibars. And so you can see you have gaps. You can see the density gets poorer as you go toward the edge. And with 18MS, it looks great. You get good coverage. You do get orbital gaps as you go further to the equator. But in the mid-latitudes, it looks very, very good. CRIS, it's always hard to compare CRIS because CRIS has 2,300 channels, and so we just simply pick one. But we talk about it by saying that it has 6 times the vertical resolving power than our old generation operational infrared instrument called VIIRS. And if you remember that bubble chart that I showed, that showed which instruments impact the most or the type of instrument for weather forecasting, VIIRS doesn't even show up on the list. VIIRS, impact of VIIRS for NWP is basically nearly zero. And with infrared sounders, it's very high. Hyperspectral infrared sounders by itself, an individual instrument, for example, if you compare one infrared sounder with one microwave sounder, the infrared sounder has the largest impact of any instrument. And so CRIS has 6 times the vertical resolving power than VIIRS, which means I can see more details in the atmosphere, which is important for forecasting. And then we have OMPS here. This shows OMPS, better coverage clearly versus SPUV, which is only really a near nadir instrument. So you can see these improvements. In terms of VIIRS, VIIRS has a much larger swath, as you see here, compared to MODIS. At the edge of scan, you can see that VIIRS is very sharp detail, while MODIS will get blurry. We can see the entire we can observe, for example, the entire Antarctic in simply 12 hours. These are 2 different orbits. Compared with AVHR, VIIRS has 22 channels. AVHR only has like 5/6, and much better spatial resolution. And this is just a one-day image. So for NOAA 20, we're operating 2 ground stations now up in Svalbard and McMurdo, which means you're going to get the data twice as fast as you got before SUMI and PP. And this basically shows the improved latency starting with NOAA 20. So here, for example, with ATMS, even though the requirement is 96 minutes, 95% of the data comes in within 40 minutes, which is remarkable because you're using 2 ground stations now, opposite poles. And before with SUMI and PP, the requirement is 147, but we got 95% of the data in 99 minutes. So some people ask, well, who cares? Does it matter? Sure, it matters. This is latency is a function of how much data gets into the model. So if you had something, and these are different models, the North American model, which is mesoscale, this is a global model, GFS, and this is the hourly, which is like the HER model. And so, for example, if you only had 140 minutes latency, which really is, according to the 95%, you're really operating at 100. You're only getting 65% of the data going to even global models. When you get closer to, let's say, 40 minutes here, now you're bringing that all the way up to 85%. So that's remarkable, right? Now, if you look at the hourly model, basically if you're at 100 minutes, you get nothing. You know, hourly have very short cutoff times, so you get nothing there. But if you get 45% in 40 minutes, you get about 40%. But we also have something called direct broadcast. So we have these stations, which we'll talk about later, that as the satellite passes over, you can get the data and process data immediately. And so we're actually driving that down to about 15 minutes with direct broadcast. And so these regional models, hourly models, only cover a small region of the globe, and you can have direct readout stations in that region to bring out the data. So we're getting now approaching 60% of the data coming in using direct broadcast. So anyway, latency is important. Okay, so these are our products. So from these instruments, we generate a lot of products. Our next speaker will talk more about this, Li-Hong Zhou. And so we have lots of products. So we have VIIRS, we have CRIS, we have combination CRIS ATMS, ATMS by itself. We also have a partnership with JAXA, where we process the AMSR2 data in real time to get other products. And so anyway, we have a lot of products. And what we have within NOAA, a program called Proving Ground and Risk Reduction, which focuses on applications, working with the users to transform these products into applications. And we'll have discussions later in today's program about the different activities that have been going on in the Proving Ground, which basically demonstrates the improved applications by using JPSS data. So we have NOAA 20, and the data is coming out already. Last month, we got the ATMS data was released. It's still pre-operational, but it was we had the first press release. So this is just channel 18. It's a water vapor channel, global from ATMS, and where you have these warmer temperatures here. That's where basically air is descending, you know, and you're getting, you know, you're seeing lower in the atmosphere. And then where you have these greener, colder channels or measurements, you're looking at water vapor, so you're looking higher in the atmosphere. You're looking at these little blue dots here are precipitation, so you're seeing the heavy precipitation because it's scattering, basically, the microwave radiation, so that's that signal. And then near the poles, you see these cold temperatures, and that's basically seeing snow and ice. So this is ATMS channels 2, 6, and 17, basically showing similar. ATMS is showing like channel 2 is showing moisture, precipitation, and this channel here is showing mid-tropospheric temperature. And this channel here is showing water vapor again. But we take this information. Now, this information is assimilated directly into numerical weather prediction models because they model it that way. But for users, for applications, we transform these products, or this is what we call SDR, sensor data records. This is like the raw data. And we transform them into products. So we go from sensor data records to environmental data records. So here's an example. Now it's more meaningful. So here's temperature of 500 millibars, which is about 18,000 feet. And so this is temperature. So you see these cold intrusions of cold air, warm temperatures in the equator. Here you see total precipitable water, so you can see the amount of water vapor in the atmosphere. And here you see rain rates. So now it's more meaningful. You can do something with this data. So that's what the algorithm program is all about, transforming, characterizing the sensor data records, making sure they're accurate, then transforming them into environmental data records, and then in Proving Ground, we take that and work with the user community to focus on applications. All right. SUMI MVP and NOAA 20 has great agreement in the beginning. Right now it's 50 minutes apart, but in the beginning they were minutes apart. And so this is NOAA 20 coverage for one particular channel, and from NOAA 20 versus SUMI MVP, they're virtually on top of each other. And these are histograms, and the instruments are really operating well, very well. So very good comparisons. So now let's show some examples of what we call environmental intelligence, looking for things. So even the primary mission of the program is to feed numerical weather prediction models, right? If you had to say just one thing about the program, that would be it. What's the primary mission of JPSS? To feed NWP models. But it does a lot more. It does a lot of critical environmental intelligence. So, for example, you can monitor ice. So as the ice is shrinking near the poles, or it's changing every year, you can monitor ice covered easily with the microwave, because I can see through clouds. So this is where you have, in March, where basically the coverage is maximum, and then in early September, where it's a minimum. And so you can see the difference, and of course, this is important for navigation, right? There's more navigation taking place in the shipping, taking place in the Arctic. Fires, this is our first NOAA 20 image. This is smoke coming out of the California fires. And this is a very impressive image here. We have a day-night band, so we can see ice at night, clouds at night, but we can also see lights at night, and this shows basically the Korean Peninsula, Japan, and you can see the city lights, you can see fishing vessels, so sometimes people use this data to monitor illegal shipping, and you can see also how dark North Korea is. So they only have one light, that's the capital, and then they have a few fishing lights, fishing boats here, but it's pretty dark there. And so we do get better coverage with two satellites, so I want to demonstrate that. So people say, well, why do you really need two satellites? And we say, well, it's a backup to one. No, it's not. It is a backup to the other, but it's very important to have two, a lot of good applications. So for example, when you're looking at ocean color and when you're looking at aerosols, you have things that happen, you have sun glint. So this is a picture of, I think the first one is Sumian PP, yeah, it is. And then you have missing data. And this is ocean color. The colors here, this is chlorophyll, basically, retrievals. I don't have a color bar, sorry about that. But you can see there's certain things that it can't do. You can't do ocean color in sun glint, right? And you can't do ocean color as you go out too far with respect to viewing geometry, because you have too much of an atmospheric correction that doesn't work so well, or atmospheric attenuation, or contamination. But now, look what happens when you have another satellite about 50 minutes apart. The colors look different because it hasn't been calibrated yet exactly, right? So don't worry about the light blue, the dark blue versus the light blue. That will change soon. But you can see this missing swath here. Well, let's go here. This is over Cuba to western U.S. And you can see, let's see, that is covered nicely. So the next orbit covers it. So basically, yeah, so that looks good. So, and then here's sun glint here, the next orbit, oops. Yeah, so this is, hold it, let me go here. Here's the sun glint here, and next orbit, I have data. So that's exciting. So with compositing of the two satellites, we'll be able to get good coverage. And this applies to aerosols too. You can't do aerosols in sun glint. Another thing I should mention, when you do soundings, our sounding footprint gets really big, as you go out to off nadir, as you go angles. So the 50-minute separation, what's happening is that when you're looking at, let's say, a far scan angle where the footprint size will grow by almost a factor of 3, about 2.5. NOAA 20, when it comes over, will be looking at that area nearer to nadir. And so now when you think about the two being used together, you're going to have very good spatial resolution and also very good spatial, horizontal sampling. And so even when I think, when we show some new CAPS retrievals, you'll see at the edge of scan that the points sort of spread out. But then the next satellite, those points will be covered by more denser populated points. So that's really important too. So a lot of good advantages of operating two satellites within 50 minutes. Okay, so we also provide what we call life-saving data. And so these are burn scars and fire and smoke from California fires. Again, we can also look at power outages. This was during Hurricane Maria, Puerto Rico, on July 24th, way before the hurricane. This is what it looks like, maximum lighting in Puerto Rico, and this is what it looked like the day after, a few days after. So it's very dark, a lot of lights, a lot of power outages. And then, of course, we can monitor the progress. So you can see from this lower one here, late October, more lights are turned on, but it hasn't made a full recovery yet. So we can use this data to also monitor recovery of power outages. We can use the data too, this is VIIRS, and we work closely with FEMA on these projects. From Hurricane Harvey, Irma, Maria, we work closely with FEMA. We provided FEMA directly with flood maps from VIIRS. This is Hurricane Harvey, and they love this data. You know, we were concerned that the spatial resolution wasn't good enough, but they said, no, this is absolutely great because it's the coverage that matters, because FEMA will fly aircraft over areas. So they'll take this data, and then they'll correlate this data to population centers, emergency responders asking for help, and they'll prioritize, and they'll say, okay, yes, this is an area of flooding, let's say in this area. We're getting distress calls. There's a lot of reports on population damage, or not population, I mean infrastructure damage. And so they'll take an aircraft and fly in this area. So they actually love this data. They said this is incredible for them for their planning using other resources. And also going back to fires, what we've been working with Weather Service and OAR on is improving smoke forecasts. So when you look at fires, you worry about fires in the immediate area, right? Damage to homes, life and property. But you also worry about fires in terms of smoke, right? Air quality, inhalation, has a lot of poor health issues associated with smoke. And so we've been taking the VIIRS. VIIRS has a product called fire rated power. It basically tells you how hot the fire is. We take that information, we put it into a forecast model called the HER, and then it predicts the smoke. And this is an example of a prediction of smoke. So this is actually surface smoke from fires from Washington State and also Oregon from last early September 2017. And you can see the progress of the fire, the smoke. And that's really important for forecasting. So this basically showed that the smoke was lifting and moving out of the Seattle area. And that's important because you have to tell people, stay inside today. If you have health issues, wear a mask. Tomorrow, it should clear up. So this is great information. So we're providing this VIIRS fire-rated power information, going into models in order to forecast smoke. And that's an example of the proving ground activity of taking products, putting them to applications. Okay, and also we can look at burn scars. This is actually from June 2014. King Fire. King Fire actually happened in September 2014, so you don't see anything there. So anyway, I'm pointing out that VIIRS is actually a great instrument for remote, land remote sensing. And then, if I look at June 2017, you know, just last, a few months ago, 6 months ago, here's that burn scar. Look at that. Also, June 17, June was the end of the rainy season. You know, California got a lot of rain last winter, if you recall. So you can see a couple differences. You can see a lot of snow in the mountains, more snow than that year. So that was a drought. You can actually see the reservoirs having less water. But you can see that burn scar. This is a burn scar. This is already a 3-year-old burn scar. And then you can see, well, what does a burn scar look like after the fire? And this is October 2014. It looks kind of strange because there's still a lot of leaves on top of the trees. So it's burning, and then eventually the leaves get swept away, and then a year later, it looks like this. So you can see that. Also, you can see how much little water there is in this area. You can see there's actually, oops, I'm flipping the wrong way. But you can see this little pond here, or whatever you call it, is basically bone dry. And then you can see that there is a recovery of the burn scar area. If you go back to this, you can see in this, this creek, there's trees flourishing again. So it's very good. It's a good instrument to monitor changes in land. You can also, for example, compare 2016 for 2017. A lot of fires in 2017, December 2017, as we know. It's also much drier in December 2017. So this is December 2017 versus just a year ago. And you can look how different it is. Look how much green it is in 1 year apart. So it's really a great instrument for land remote sensing. Again, these are the wildfires. This is a false color, basically using thermal IR, so it's not really this green, so don't discount that color. But anyway, this shows the imagery showing how hot the fires are and the smoke coming out. But again, we don't want to just show imagery, we convert these to products. And so this is an example of aerosol optical depth being generated. So now you'd have a concentration, you have from a qualitative measurement, now you have a quantitative measurement that can now be used in models. And we also use the products in tandem, I mean the satellites and instruments in tandem. So a lot of people care about aerosol optical depth. They also want to understand the CO, how much carbon monoxide is coming out. And this is an example here of a new caps retrievals, which we'll hear later today. And so this is what I was talking about, the points spreading apart as you go off nadir. So once we have NOAA 20, these points will be replaced with points that look more like this in this area. So anyway, this is a CO profile, and you can see a high concentration of CO. You can see that the CO is lower in the atmosphere. So it's really important that we start using the instruments not separately, but together in tandem. And now other applications, like for AVHR, for many years, we've developed a Vegetation Health product that basically is looking at greenness minus a 30-year climatology. We're going to expand that, continue that with VIIRS, which provides higher spatial resolution. This information is actually used by USDA, United States Department of Agriculture. They use it every month for their agriculture supply and demand estimates. So you can imagine VIIRS for the next 20 years will providing critical data for monitoring food security, for example, critical application. I didn't mention too much about fisheries. This is an example of ocean color from along the Gulf of Mexico, just one example. And people have done studies looking at ocean color, chlorophyll, and this is an example of like, there was a forecast, they forecast like the return of the Chinook salmon in the Columbia River. And the forecast was much higher than the observed return. They didn't have that much. And then they looked at the study, looked at a little bit more, this is back in 2011, and they noticed that the chlorophyll production, the amount of chlorophyll in the Gulf of Alaska, was much lower in 2011. So now they're trying to make the connection now. Chlorophyll, less food nutrients, less salmon. So now we're able to start doing more of these studies for fishing applications, fish stock assessments. Just a couple more slides. I didn't show anything from OMPS. This is OMPS aerosol index over China. This is what it looks like at the ground. I don't think you want to be there during that day, even though there's a lot of people at the Forbidden City. And, but you can see what it looks like from space, right? And so that's really important. We'll be able to track air quality from space for many years into the future. International collaboration is important. I just talked really about JPSS, but part of JPSS, we have a JPS, which is Joint Polar Satellite Agreement with EUMETSAT. So we work together with EUMETSAT. They provide similar data, and they'll have a new generation of satellites starting in the early 2020s. And they cover data in the mid-morning, 9:30 orbit. And together, there's a lot of advantages of doing this. This is an example of using data from NOAA 1819 METUP A and B and SUMI and PP of total precipitable water. So remember I showed you that static image from ATMS? People like animation because you want to be able to see flow as well. And so this is taking TPW from those sensors, total precipitable water, fusing it with a forecast model because the forecast model is pretty accurate in terms of steering currents. And then you fuse them together and then you can see through clouds, right? I'm not being, I don't have to contend with clouds obscuring my view, but I can see these large atmospheric river events coming from this typhoon in the beginning, all the way hitting the west coast. So this is a great example of how we can use polar satellites, fuse them with forecast information, and start looking at data in near real time. So to conclude, we launched one already. We have 3 to go. The instruments are doing really well on NOAA 20. We'll hear more from Lee Hong in the next presentation. And thank you very much. And if you want additional information on the instruments, because I didn't really go through the details, you can go to the JPSS website shown here for more information. Thank you.
Thank you. Thank you, Mitch.